What are the chances of winning and losing when playing blackjack in Las Vegas? Here is the example of a blackjack player that has a strategy that provides an average of 48.5% chance winning a hand. So the probability of winning a hand is 0.485 according to numbers given here. This player plays on average 45 hands per hour, and he keeps or she keeps playing for 6 hours. So the total number of games played is 6 times 45, which translate to 270 games played in 6 hours. Suppose that there is a $100 bet per hand. So the first question is how much money this player wins or loses on average after 6 hours. Okay, I'm going to answer these three problems using binomial distribution, but then I'm going to show you that there is a good approximation of binomial distribution to answer ABC using normal, as is illustrated on these PDF plots. So these probability distribution and density plots are the ones that I'm going to talk about them later. So let's jump to problem part A. So the question is how much on average are we winning or losing? So you would say the average times that we are winning, mu or x bar in this case, is if you play one time, the chance of winning is p or 0.485. If you play 270 times, obviously is n times p, which is 270 times 0.485, which approximately is 131. So that is the average number of times that you're going to win after you play 270. Now, okay, this is number of win. So what is the number of loss? Well, number of loss is the total number, which is n minus win, which is 270 minus 131, and that is 139. Okay, every time you lose, so before that, what is the net loss? So net loss is the loss minus win times the bet, which is $100. Well, loss is 139, win is 131. So loss minus win is 8, and times 100 give you $800 total net loss. So after playing this game for 6 hours, on average, this player is expected to have lost $800. That's the answer for part A. Effectively, what we are saying is this variable x, which is number of times that the player is winning after 6 hours. It's a discrete binomial random variable. Binomial because every time you play, you're winning or losing. You're fading or you're, let's say, passing the game. So, therefore, the outcome is a binomial distributed random variable, which we say is binomially distributed, and it has a mu of np, that is just obtained above, roughly 131, and it has a variance, which is np times 1 minus p, which is, if you compute, it becomes as simple as this variance. So I'm going to compute it here, equal to 270 times 0.485 times 1 minus 0.485, and this is the variance. And if you want to find the standard deviation, that's not difficult. You would say standard deviation, naturally standard deviation of random variable x that is binomially distributed is square root of variance, which is the square root of the number that we just found here, and that is equal to square root of this number, which become 8.212 roughly. So I'm gonna just highlight this and also highlight this. So these are the standard deviation and variance for this binomially distributed random variable. Now let's move to part B. What is the probability that this player loses 1500 or more? Okay, we're gonna move to part B, and in this case we are saying if you're losing at least 1500, since per game or every time we lose we are losing $100, that means the total, the situation we have is let's say net loss in terms of number of times that we are net losing is going to be greater than or equal 15. Okay, so what is the meaning of this? The meaning of this is loss minus win should be greater than or equal 15, while we know that loss plus win, the total number of winning and losing together, should add up to n, which is 270. Okay, what is the meaning of this? The meaning of this obviously is we have to have at least then 285 if we add up these numbers together. The meaning of this is turn out to be, let's say 135 is the minimum. So let's say 135, then add together, you become 285 divided by 2, and it will give you 143, let's say. If we have at least 143 losses, then it means the win for this game will translate to 127 or less, which exactly satisfy the requirement that we have in mind. Okay, so if that is the total number of loss, it means total number of win will be less than or equal, as I said, 127. Okay, so what are we computing? The question that is asking what is the probability of player loses 1500 or more is effectively the question that what are the chances that the number of winning is less than or equal 127. 128 is not an option, because if you go 128, then number of loss is 142, the delta is 14, is not going to satisfy. So the maximum win acceptable is 127. So how do you find this? Well, that's the good question. If you're directly using normal distribution, the binomial distribution, there's a good formula for this. So in Excel, you do binom. So what you do is you would say equal to binomial.dist. And as you can see, it will ask, hey, what is the number of success that you're interested in? And you would say, I am interested in 127, as the question is here asking. What is the total number of trial you're doing? So you would say let's say, so the total number of trial is 270. And what is the probability? And for that is P 0.485. And are you doing cumulative? Yes, this is W less than or equal 127. We're not saying W equal to 127. Therefore, we have to say yes, compute the CDF for us. There you go. So this is effectively saying that there is 33.7% chance roughly that there is this chance that, let me just reduce this so that you can see. Okay, so there is this much of a probability, or 33.7% chance, that the player end up losing more than at least $1,500 or more. So if you do it with binomial, this would be the answer. But if you want to do it with normal distribution, interesting is, let's focus on, for example, a problem. Maybe the best visualization for the illustration of what I'm trying to say is this one, simple. Let's say you're interested in number of win to be, let's say, less than or equal this number here. So so it's 5, 6, 7, less than or equal 8, let's say, at the center. Now, what you do from perspective of normal distribution. So you want to, effectively, if you're using binomial, what you're counting in this scenario, if you say what is the probability of 8 less than or equal 8, x is less than or equal 8, you would say find this area using binomial. That formula that I showed you is effectively adding all these blue areas together. When we are using normal approximation, what we say is, okay, go 8.5, which is this point. This center is 8. Go 8.5, go up, hit the normal distribution, which is this line, and then compute the whole area under the distribution, under the red. So whatever you find is the approximation for p of x less than or equal 8 using binomial. So in this case, if I am using, this one is the probability of x binomial less than 127. If I'm approximating it with normal, then I have to say probability of x normal less than or equal 127.5. And I am using the mu for the normal distribution of 131 and variance of 67.44 or a standard deviation of 8.2 for normal. Why am I saying this? Because when you go and use the approximation from normal distribution, you have to use norm.dist. If you don't want to use the standard normal, I'm using just normal. So it would say, what is the value of the variable that you're interested? 127.5, 127.5. And it would say, what is the mean? Okay, I showed you the mean is 131. And it says, what is the standard deviation? 8.212. 8.212, roughly. And is it cumulative? Yes, it's less than or equal that I'm interested in. So it's cumulative, so it has to, the fourth argument has to be true. Okay, see, my approximation using normal distribution approximation turned out to be not that far away from, it's relatively close for the actual number that we found from the binomial distribution. Okay, let's move on to then, let's move on to part C. So in part C, what are we doing? What is the probability of that the player wins? Okay, if you want to win, what are you saying? You're saying that win should be, you want to win. So number of wins should be more than loss. And so what is the meaning of this? It means win minus loss greater than or equal 1. But we know win plus loss is fixed number 270. That's what we know. Okay, so let's add them together, and from these two, what do we find? We find that number of winning should be greater or equal 135.5, which is, I mean, when you say should be greater than or equal 135.5, naturally it means that number of winning should be greater than or equal 136. We don't have any other choice. So that's what we want. The question in part C says, what is the probability of player winning? It's not saying that what is the probability of player end up with win and loss the same. So, okay, if that is the case, the question basically turn out into this. The probability that win is greater than or equal, the probability that winning, which is x binomial, is greater than or equal 136 times. This is equal to 1 minus the probability that x binomial is less than 136, which means less than or equal 135. That's the complement situation. Okay, I'm writing it because it's CDF and it's not difficult for me to compute it. So one way is using binomial, and as I showed you, if we use the binomial formula, it will become, let me put it this way, I am going to use binomial formula, which is this formula. So equal to binom.dist, and as before, number of trial 135, number of these successes 135, trial 270, and probability 0.485, and cumulative true, because I'm saying p of x less than or equal 135, so true. And I am doing 1 minus this, so let me just copy paste this value so that I show you later. But if you compute this, this is the number you get. So I'm gonna just post it here so that you remember how it is. Let me just post it here. So I'm gonna post it here. This is how we got it. Okay, the second method of finding the same thing is this method. So let me just make sure I'm not missing something. Okay, great. So the second method is this method, normal. So 1 minus norm dot dist, and we have, since we are shooting for 135, we have to go to 135.5. This is referred to as continuity correction factor, as I explained when I was talking about the part B. And mean is 131, and standard deviation is 8.212, as was found here, and cumulative true. See? So 0.29185 is not that far away from 0.2896. Both of them roughly about 0.29, indicating, so let me also copy paste the formula here so that you know what I did. So the formula is this formula. If I'm using normal approximation of binomial distribution according to the concept I explained using the 3 plots here, then I'm using this formula. As you can see, it's not that far off from the actual probability computed using binomial distribution. So there's about 29% chance that when this player plays for 6 hours straight, effectively for 270 games of blackjack, then the player ends up winning the game, at least by 1 game. I hope that this example is helpful in terms of illustrating the use case of normal approximation for binomial distribution using the example of playing blackjack in Las Vegas.